checking out the Six Sigma Tool Guide. Today, this is kind of part 3 in a discussion about hypothesis testing, calculating chi-square, and approximating p-values. If you haven't seen part 1 and part 2, you might want to check that out first. This video really sort of assumes you're familiar with how to do those calculations, and this is really just practice interpreting results and kind of validation for the tool itself. We're going to do some make some common sense experiments and see if the p-value backs up what common sense tells us. So, alright, so let's go ahead and get started. So again, the purpose of this exercise really is just to practice interpreting results from hypothesis testing. We're going to try and demonstrate the accuracy and power of an approximated p-value. We're going to test the validation process. We're going to use a simple illustration with dice to sort of test the p-value's power of determining whether the changes we made were significant or not, or if we're just seeing a sort of fluke random chance improvements. We're going to ask if this statistical tool can correctly determine if our process change was significant or not. We're going to test that ourselves because we'll know whether or not the changes we're making are. And we're going to kind of just validate that statistical tool. It's statistical tool validation versus common sense validation, and do they get the same answer? Alright, so a little background on this exercise. For the sake of this experiment, we're going to say that we've been asked to deal with a very specific pain point. The federal law requires that all new hires get certified in their specific job function prior to beginning work. So the current process involves taking a training class of 20 new hires and covering very specific training material and then testing them at the end of the week. And those that do not pass that test with an A have to take the training again the following week, and so on and so forth until they do pass. So this project is to improve the training process and increase the number of passing students on the first week. That's the primary metric. So we want to reduce the wasted time on retraining, get folks started as soon as possible. So we're going to pretend that we have 3 separate possible solutions, and we're going to take 3 pilot programs and see which ones yield us the most statistically significant results. And we're going to use a p-value to approximate that. And this is going to be a good example of testing that validation process and proving that it does work. Alright, so we are going to practice doing some hypothesis tests. We're going to use dice to determine the scores of the students' tests. And really the only thing that matters is a 6. We want to get a 6 or higher. That means that the student passed the test with an A or better. Everything else is really just varying degrees of failure. Our primary metric is going to be how many people got A's, which is going to be how many times we rolled a 6 with the dice. So the current process. We're going to throw one 6-sided die with our right hand to represent the current training process, and we're going to use those scores. So if we roll a 6 or higher, that's a passing grade, and that allows that employee to start their new job. Anything less than a 6 means they have to go through training again next week. That's the pain point we're trying to mitigate. So we're going to roll this one die 20 times to represent the 20 students, and we're going to record each of those scores as our expected results that are typically achieved with the current process. So here we go. We had 2 people out of 20 that scored a 6 or higher. This is using the old training method, so this is our normal, par for the course, expected results that we want to improve upon. So for pilot program 1, for this illustration, we're going to make a change that you and I know is meaningless. We're going to use our left hand instead of our right hand when we roll the dice. So this is pilot program 1. And this is meant to represent a change that you and I in real life know is not going to make a significant difference. But the chi-square table doesn't know this. So we're going to make a meaningless change, we're going to record our results, and we're going to kind of test the table. We're going to see if the chi-square table is smart enough to say, yeah, you know what, this was not a significant change in the process. So for the sake of the exercise, we'll say that the training took place in a different room. That's what pilot program 1 is. We changed the environment, same trainers, same methods, we just got them in a different room with better light. So we're going to roll the dice 20 times, and that's going to represent the 20 students who were part of pilot program 1. We'll record these results as observed results 1. So I've taken those results from our pilot program of changing the room where the training is taking place. In real life, we just switched hands to a left hand when we rolled the dice. But look at this, we've got some improvement, it seems like. The green represents the pilot programs. You can see there was a 50% increase in passing grades. There was a 200% increase in near passes. You see all of the low scores went down. So it seems like we're on the right track. Using the left hand instead of the right hand apparently gets you higher scores when you roll the dice. Probably not. Don't kid yourself. And this is what we want to avoid with hypothesis testing. Don't let early indications of success sort of seduce you into thinking that this was a significant change. The reality is, yeah, if on a bar chart it kind of looks impressive, but the old process was getting us, 2 passing grades, and the new process is getting us 3. Is that statistically significant? I don't know. We're going to test it. Again, increase in near passes, is it statistically significant? Probably not. We're probably not on the right track. We probably just got kind of lucky. But that's the purpose of this test. Let's see what the chi-square table tells us. So here we are with Pilot 1 results. Again, as I mentioned, they are better. We used the left hand instead of the right hand. We got 1 extra 6. We got a couple extra 5s. There was a decrease in the lower scores. But common sense tells us, you and I know, that just using our left hand instead of our right hand is not going to consistently give us higher scores. So let's do the math and see if the chi-square table can come to that same conclusion. If we follow the steps, we're going to get a chi-square value of 3.03. And with 5 degrees of freedom, a distribution table will tell us that our p-value is between 0.5 and 0.75. So a p-value between 0.5 and 0.75 means there's a 50 to 75% chance that these improvements, quote unquote, are just random chance. It's just a fluke. So it's telling us we should accept the null hypothesis that this process change did not produce significant changes. Although the scores are better, it's not statistically significant. So we should accept the null hypothesis. This process change did not have meaningful impact. And common sense says, you and I know, changing from the right hand to the left hand, that should not give us anything significantly different. So on to pilot program number 2. This time we're going to make what you and I know is a very meaningful process change, because we're going to use a 12-sided die instead of a 6-sided die. And remember, anything higher than a 6 is a passing grade. So common sense tells us we're more likely to get a 6 or higher using a 12-sided die. Chances are about half the rolls will be 6 or higher, because there's only 12 options. But again, chi-square distribution table doesn't know this. It doesn't know what we're changing. It just knows we're trying out a different process and we're going to get different results. So it's going to look at those results and help us determine whether it was a significant change or not. So for the purposes of the exercise, we'll say that pilot program 2 is about using some new training material. And we'll roll the dice 20 times with the 12-sided die, and we're going to record our results as observed results 2. So here we have observed results 2 from our second pilot program. Like you'd expect, we got lots of scores that were 6 or higher. In our imaginary scenario, we said we just have new training material. In real life, we switched to the 12-sided die. So yeah, common sense is going to tell us, yeah, this is a significant process change. We should be getting a lot of extra 6s. But if we follow the steps and we do the math, we're going to get a chi-square value of 51.02. And with 5 degrees of freedom, a distribution table will tell us that our p-value is less than 0.001. So what does that mean? A p-value that is less than 0.001 means there is less than a 0.1% chance, so that's about 1 in 1,000, less than 1 in 1,000 chance that these improvements are just random. These are statistically significant changes in results, and we would reject the null hypothesis. This process change did have meaningful impact, so we're going to accept the alternative hypothesis. Okay, so for pilot program number 3, we're going to make what you and I know is an even more significant process change, because we're going to start using a 20-sided die instead of a 6 or a 12-sided die. So again, common sense tells us we are way more likely to get a 6 or higher roll since we're using a 20-sided die. And in fact, most of the rolls will probably be something greater than 6, because most of the sides are greater than 6. So again, the chi-square distribution table doesn't know this. It just knows we're making a change and we're getting different results. So we're going to record these results of this new process and see if the chi-square table recognizes that yes, hey, whatever you changed is significant. The table should even demonstrate that this is an even more significant change than on pilot program 2 when we had the 12-sided die. So for the purposes of this exercise, we're going to say that program 3 involved using that new training material, and there's a new method because they're going to do some job shadowing before they take the test. So here we are. Pilot program 3 definitely have improved results. We have lots more 6s, just like you and I knew in the real world is common sense. In our imaginary scenario, we added job shadowing to the training, and this is what it did to the scores. So in real life, obviously, we just switched to a 20-sided die, and the common sense is going to tell us, yeah, that's a very significant change using a 20-sided die. So if we follow the steps and we do the math, we're going to get a chi-square value of 81.07. And with 5 degrees of freedom, that table is going to tell us that our p-value is far less than 0.001. So a p-value this low means there's about a 1 in 100,000 chance that these results were just some random fluke. Any p-value less than 0.05 really gives us the ability to reject the null hypothesis. So we're going to reject the null hypothesis, and we're going to accept the alternate hypothesis that this process change did have meaningful impact on our results. So in summary, p-value less than 0.05, that's going to give you confidence that the process change you made is yielding results that are statistically significant and not just a fluke. The reliability of that p-value can be tested like we've demonstrated here today. And so remember, in this experiment, we had complete control over these pilot programs. We knew that using a 20-sided or 12-sided die, we're obviously going to produce more 6 or higher rolls, but the validation tools didn't know this. They simply read the data and gave us objective analysis on whether or not those changes in performance were significant enough to be attributed to process changes over random chance. And that's the key here. We want to avoid that bar chart slide where we see early indications of success and we pat ourselves on the back and say, good job, and we move on to the next project. We need to ensure, and that's what's so important about hypothesis testing, we want to ensure that those changes that we made to the process are yielding statistically significant results, results that are really moving the needle and not just, possibly a fluke. Well, I hope you found this helpful. Check out some of our other videos on various Six Sigma tools, and if you have any questions, please reach out to anyone on the Process Innovation team. Thank you.